Thank you for the invitation. So I should start by saying that I don't actually work on localization. I don't work on quantum mechanics either. I'm more in the regime of molecular mechanics, so the nuclei, not the electrons. But there's one specific aspect that comes into play here whenever you try to develop coarse-grained models that where I develop sort of a tangential interest in a question that is, I think, closely related to the sort of localization questions people have talked about. And I'll get to that eventually. I'll first start by introducing the problems that I am actually interested in directly. At the moment, so this is one out of a large class of similar and related problem. It's how you develop interatomic potentials as models coarse-grained from electronic structure models. So not as independent models in themselves, but as approximations to quantum chemistry. That is the question, and I'll say a little bit about how that looks like. So at the end of the day, I do not care about electrons. I care about having a potential energy surface. So given a collection of particles, I want to be able to evaluate the potential energy surface, and if I can do that sufficiently accurately, sufficiently fast, then I can perform all sorts of molecular modeling tasks, compute stable equilibria, run molecular dynamics. This is supposed to mean compute transition paths between stable equilibria, so diffusion, or just sample from some interesting measure on the space of configurations. And we know what good potential energy surfaces are. They come usually from electronic structure models, quantum chemistry or DFT, and the upshot is you have to solve an eigenvalue nonlinear eigenvalue problem, and that kind of limits what you can do with them. So this is sort of where most of this workshop was, and what I'm interested in is how can I develop potentials of this kind, potential energy surface of this kind, that get as closely as possible to electronic structure. So what is the difference here? Here the potential energy surface is given as some complex function. I'm not even writing it down because it's not actually too important for most of my talk. I'll say something about that later, of the energy levels that the electrons can occupy, and depending on what the model is, maybe also the orbitals themselves. But I want to write the energy in a way that highlights the spatial structure. So I write it as a sum over all the particles in my system, and then from each atom, so let's say the red one here is with the one with the index I say I want to give it an energy contribution that depends on a small interatomic neighborhood. So these Rij's here are all the distance vectors. That already makes quite a few assumptions, right? I mean, should one be allowed to do that in the first place? But models of that kind have been very successful for many, many decades. But they're sort of experiencing a bit of a revolution right now. So the classical models look roughly like this. These are the ones from the 20s, 30s, and so on. So it's sort of a mixture of ad hoc derivations and physical insight, chemical insight, good guesses. Lots of things go into this, but in the end you try and write down a simple functional form. So for example, one popular potential is called the Morse potential. You say, okay, all particles interact only through a two-body interaction. Of course, much too simple, but for the sake of illustrating what I want to say, this is good. So I know that the atoms want to repel and they want to attract, but not too strongly. So if they push them too far apart, then the attraction gets weaker and weaker. And there's a reason for why I put an exponential here. There's why I put double squared exponential here. There's no good reason. But at the end of the day, I have a shape for this potential, and in the shape I can identify three parameters: the depth, the width, and the equilibrium distance. So it's very simple, very easy to interpret these, and it's very easy to fit them to experiments or accurate data. So now what has changed now over the last 10, 15 years maybe is going away from this very simple form, a handful of parameters, to, they call it machine learning type models. can use that term. I'm not sure it's an entirely accurate description, but anyways, you use functional forms that are completely generic. So rather than say, okay, my interaction is only through two-body and maybe three-body, maybe an EAM type term for those who know what that is, I say now that this contribution to the potential energy surface is some functional form that can in principle describe any potential of that kind. Okay?
Excuse me.
Yeah.
So the R represents the position of the center of mass of the atom.
The Rij, so I is the center atom,
yeah.
and the Rij are the difference vectors.
I mean, you don't look at the electron. You have no electrons here.
That's right.
You have neutral atoms here.
I want that at the end of the day, the electrons will be in that functional form.
The electron cloud is hidden within the potential.
I want to evaluate the potential energy surface without solving the electronic structure problem.
Okay.
That's the goal, all right? But we're not there yet. I'll get to that in a second. But for the moment, I'm postulating, I haven't shown this yet, but I'm postulating that I can take this potential energy surface, I can rewrite it in that form up to some error that I can hopefully control. And then and therefore, because I'm making this very strong requirement, I now choose a generic approximation scheme rather than a simple interatomic potential in order to model that energy contribution. Okay? And you know, the people in this field, they learn from the computer scientists. So, you know, the first group that does this, they train a neural network. The second group that does this, a Gaussian process. Sorry, you had a question?
Yeah, now the parameter C, is it, before it maybe just was a subscript letter, it was just a radius, which was all you cared about, and now it's sitting there. Is this a collection of parameters?
Bold
a vector of parameters?
is an, in principle, infinite collection of parameters. That's the point.
Right.
So rather than having 3 or 10 parameters in classical potential, you now have tens of thousands, possibly more parameters, and that allows you to, in principle, fit anything you like. That's all that happens. So it's the same idea as before, just you make it completely general. Okay. I keep the idea that I can decompose my potential energy surface into simple components. And in this case, I mean, we can talk about what simple components mean, but in this case, I require that I can decompose the potential energy surface into localized contributions from small atomic neighborhoods, overlapping. Okay. That's somewhat conceptually easiest way to describe this. Okay. So in principle, this is what the workflow, how you do this. So we've chosen an approximation scheme for, let's say, a neural network. I'm not going to do neural networks, but everybody loves neural networks, so let's choose a neural network. So the next, now you need to somehow fit the parameters. So you need a training set. So for example, you see here, this is a training set. You generate this is silicon, bulk silicon. Let me go back. It's such a nice video. So you just generate thousands or possibly millions of silicon configurations in small configurations that are small enough that you can actually evaluate the DFT model, or possibly even quantum chemistry if you can afford that. But this is DFT. Okay? So in this particular training set, there are 3,000 configurations that essentially cover the entire phase diagram of silicon, which is non-trivial. Right? That comes down to, when you take all the energies and all the forces and all the stresses that come out of these configurations, comes down to about 500,000 scale observations that you can make out of this training set. So then you stick your functional form that you've chosen on the previous slide into a simple least squares method. Right? You just sum over all the observations you've made and minimize the root mean square error. This is usually called force fitting, and that's what it looks like if you write out explicitly what these observations are. Then there are weights in there and so on, but those are details that are important. So once you've done that, you've determined the parameters. You can then have your fitted potential energy surface, and now you can run simulations, large-scale simulations that go far beyond the small training sets you have here. Okay, so this is not large scale, but it's large enough just to exploit this. So, and in a way, this is quite an extreme case of generalization. So in traditional machine learning, you have you generate you have lots of training configurations, and then the configurations of which you then make predictions are all very similar to your training configurations. Here now, I'm training on a set of very small, simple configurations, and then I'm making predictions on arbitrarily complex, large simulations. That's somehow the interesting aspect, or one of the interesting aspects in this. So it's a non-trivial step, being able to train a potential energy surface on small configures like that, but then evaluating it, and trusting that evaluation on arbitrarily complex and large configurations. Okay. So I'm not going to go into all the details of that, but I'll show some aspects of why that is possible. All right. So maybe just very quickly, what can you achieve with that? Well, so this is somehow the case for these machine learning type interatomic potentials. What you see here is a range of different interatomic potentials. So DFTB, that's sort of something in between density functional theory type binding and fitting some parameters. And then a few other potentials that are quite popular. And GAP is a Gaussian process regression scheme for which this silicon database has been developed. And here you see a few material parameters. It's not important what they are, but the main point here is that each of these potentials gets one or two accurate properties which have been fitted. And the advantage of these generic approximation schemes is you can now fit anything you want. Right? You have a material property you want fitted, well, stick it in there, and you will get it accurately. That's basically it. I mean, if you have sufficiently many parameters and sufficiently rich approximation scheme. Okay, so the limitations, of course, the computational cost that comes with that. So much cheaper than DFT, but much more expensive than traditional interatomic potentials in this class here. So for example, the silicon potential, let's talk about, 100 milliseconds per atom is the cost. It means if you want to run a simulation with 1 million atoms to evaluate the forces on one configuration takes you a day. So you still need supercomputing resources and so on and so forth. But these are the kind of things that we're working on, that we're improving, that we're trying to fix. Okay. And I resisted a very long time. So one of the developers of this potential is a good friend of mine, and he's here in Cambridge, in fact. And I've resisted a long time getting into this field because I thought this is all statistical learning, and why would I be interested in becoming a statistician or a computer scientist? But there are some really fun mathematical questions in there. Approximation theory is really quite fascinating, and I will show a very simple example of that. But then the part that I want to talk about mostly today is justifying the functional forms that we use. So for example, can you justify the spatial decomposition? Okay. So in this decomposition also I have a cutoff radius, right? So I have to say how many neighboring atoms should I include, and that is exactly the localization, or the aspect of localization of interest. So I'll start with a little bit of the approximation theory. And I want to show this for a simpler problem. So let's say this is essentially, you can think of this as the one-dimensional case. Imagine you have a function. You don't have to think about interatomic potentials for this in the next slide, but just imagine you have a function that depends on j coordinates, x1 to xj, and the only feature from interatomic potentials that we keep is that they are permutation invariant. So if I take two atoms and I exchange their labels, I exchange their positions, then the potential energy remains the same if they're of the same species. Okay. So that's what I've encoded here. And now I want to know is what effect does that have for approximating these functions. And in the setting of polynomials, this one can see this extremely nicely. So let's say we take this function, we approximate it by a polynomial of degree m, and I should emphasize here, this is a total degree, so this is a sparse grid approximation for those who are aware of what that is. But it's not so important for the rest. Okay, so some coefficients times the product of the monomial. So this is a multivariate monomial. This is your standard multivariate polynomial approximation scheme. And then what you find is that this symmetry here translates to a symmetry in the coefficients. Okay, so it doesn't have to be in there a priori, but you can always enforce it without losing accuracy. Let me put it that way. So the question is, how can I exploit that? Well, I can say the following. I can, instead of taking all k tuples, so the k's are these powers here, I only take the ordered tuples, right? Because all the permutations are in coefficients anyways, so I can just sum over the permutations instead. And now what I gain by going from here to here is I have far fewer basis functions. So this is, in high dimensions, if J is large, so let's say I have 30 neighbors, 100 neighbors that are important, then this is a very high dimensional approximation problem, so you have many, many basis functions. But by doing that, you really reduce that number significantly. I'll show you in a minute by how much. But you haven't gained anything in terms of what is the cost of evaluating this polynomial, because, well, you still have this sum over all permutations, so you get this J factorial in here, which still kills you. And the trick is the following now, that in fact you can exchange summation and product. Of course you cannot, but still you can. So here's what you can do. So this is, suppose you have two particles, right? So you can do the calculation this way or the other way, it doesn't matter. Forget this for a second. Take x1 to k1, x2 to k1, x1, k2, x2, k2. Write it out, and then you have x1, x2, x2, x1, k1, k2, k1, k2. So this group here is exactly that, if j is 2. So sum over permutations, 1, 2, 2, 1, to power k1, k2, k1, k2. So that's the right ones. Okay? So this here is the blue group. And that here is a product over sums, correct? And this one here we ignore. Okay. So there's the interchange, product sum. So this sum here is that inner sum here. And I'll talk about that in a second. So now what you've gained this way is this sum over all permutations is gone. It becomes a sum over just the number of particles. So the cost of evaluating that here is much, much lower here. So this J factorial is completely gone away. It's purely this permutation invariance that gives you this. Okay, so now what happened to that? Well, this is why I write CK here and CK prime, because all that happens here is this is a group again of the same kind as that group, so you can just hide it's somewhere else in that sum. Okay. And this is a way how you can understand why approximating symmetric functions is much, much easier than approximating general high-dimensional functions. There's a huge gain in this. Okay. Why do I call this the density trick? Because what you have in here is in fact the projection of the density of the nuclei onto a monomial, onto a polynomial basis. And this idea comes up in a lot of contexts. I mean, this is not my idea. I'm just trying to understand it in terms of in the context of approximation theory. But this comes up all over the place. Okay. And there's now one other little trick here that one can do is one can say, okay, instead of taking the product up to capital J, I restrict that product to some n, and that for example is another approximation that is very popular in chemistry and physics, that you restrict how many particles are allowed to interact at any time. And you can interpret that in terms of sparsifying your approximation. So a lot of connections one can make between the two, which is very nice. Okay. All right. So there's a 3D version of this. It's a little more involved, so I'll just sort of flash this for a few seconds, and then if anybody's interested, I can say more later. But basically, you need to you project the density onto onto one particle basis, which splits into a radial component and an angular component. For the angular component, you take spherical harmonics, and that's because we understand how spherical harmonics rotate, and that allows you to encode rotational symmetry, or in general isometry. So if I take a cluster of atoms and I rotate it, then the energy is not allowed to change, and this is easy to encode if you use spherical harmonics there, and then basically your representation of the potential is the same as what I showed in the last slide, but in terms of these A KLMs instead of just monomials. And you can try and be clever about this and choose the sort of the right kind of orthogonal polynomials in here that helps a lot with stability, and so on and so forth. So there's a lot one can do to tweak this and fine tune this, but that's the basic idea. And then sort of our understanding of how spherical harmonics rotate helps us then to put constraints on these coefficients that guarantee rotational invariance. And that way, you can construct the basis of permutation and rotation and reflection invariant polynomials, which is exactly the sort of scheme you want in this setting. Okay. And the cost estimates are the same as before. I won't go through that, but it's computationally extremely cheap. And once you do go through all the algebra you need to do that, and the combinatorics, the counting exercises and whatnot, funnily enough, that goes back to some old number theory questions from the 20s. But people have solved them in the 20s, so there's not much to do here, just to find the right questions and the right answers. And you can then prove results of this kind.
So you chose an axis, that is, you have a vertical and for the spherical harmonics.
Correct.
You're picking.
Yes, but the basis itself is actually rotation invariant. So
Right,
it doesn't matter what the axis you choose. So I was a bit.
Depending on how you organize the spherical harmonics.
Yeah, that's correct. So I was a little bit quick in going through that. But so I've written this here in terms of a constraint on the coefficient, but you can equivalently implement this in terms of an actual rotation invariant basis. In that case, yes, you choose the axis. Initially, you have to choose it somehow, because you have to define the spherical harmonics.
That's what I mean.
But then you rotate over, you average over all rotations, and you end up with a basis that doesn't have an axis anymore. Yeah, so if you, now I can't write. Anyways, the point, yeah? So if you take, imagine you take a polynomial that's of two particles.
If you average a spherical harmonic, you just get 0.
One spherical harmonic. But take a product of two spherical harmonics. One
pair
particle,
products.
second particle. And now you average over all rotations, okay? So you get the stuff with the D matrices and all of that.
Right.
And okay, very good. And so for 2, it's a trivial calculation. For arbitrary n, one has to work a bit. But the physicists have done it all, and it took me a while to learn it, but I now understand it as well. Okay, all right. Yeah, okay. Okay, so here's the result that I was after. So I was really trying to explain why one can fit interatomic potentials, because I thought this is complete madness. You live in 300 dimensions, maybe 1,000 dimensions. This is not tractable. You cannot possibly approximate functions in such a high dimension to any serious accuracy. And basically constructing this rotation permutation invariant basis helped me understand where these cost savings come in, and then with a bit of work, as I say, you can prove results of this kind. So I'm calling this a meta-theorem because there are various combinations of starting assumptions I can put down, and if you want to become precise, please tell me. I will get a little more precise later on. But basically the result is the following. That first of all, I can decompose the quantum potential energy surface exactly into localized contributions. Not always. There are assumptions in here for some models, not all of them. Okay, I want to emphasize that. And moreover, this site energy can be approximated with these permutation rotation invariant polynomials, and the approximation error can be controlled in terms of the cost of evaluating them. So what this alpha is, we don't know, but it's positive. We can estimate it numerically, but I'm not going to go into that. Okay. And there are essentially three approximations one has to make very carefully in order to get that result. The first one is one has to truncate the body order, so how many particles are allowed to interact at once, at most. So that's the first approximation, and one has to control the error you make by doing that. The second, and that's a form of sparsity, and I decided not to talk about that because I'm doing too many things already. The second one is you have to truncate the interaction range, so how many particles. So here everything interacts with everything, but now I have to truncate how far out the interaction actually happens, the cutoff radius, and that's what I want to talk about next. And then the third approximation is truncating the polynomial expansion. And this is sort of more classical approximation error analysis. And if you can put them all together, then you get these sort of estimates. Okay. And they match what we see. So this here is here we're fitting one of these polynomial potentials on a training set for Gaussian process. There's a training set for tungsten that was developed for Gaussian process potential a few years ago, and we sort of refitted on the same training set, so number of basis functions against the error we're committing, and you see sort of a perfect linear rate on the logarithmic scale, so that matches the prediction. The stars are, by the way, the potentials to look for. The triangles are a different one. I just didn't have that available right now. And maybe the interesting thing here to point out is that so the different colors just means different choices of body order, and we're trying to optimize what is a good body order to choose here. The interesting thing to point out here maybe is that the target accuracy that we're aiming for, which is roughly around here, let me highlight that, that's the accuracy of this gap potential, because that's what we want to match. We get that with, let's see, maybe 0.5, 0.6 milliseconds per atom's cost, where the gap potential we measure to be about 50 milliseconds. So you know, with this classical polynomial approximation scheme, we get a factor 100. That was nice. But this is, in a way, it's an easy training set. So much harder training set was the silicon potential that I mentioned earlier. Okay, so how far can we get there? This is more challenging, but we can still sort of reach the same accuracy at lower cost. There's about more work we have to do to optimize this, so we don't get quite to the 0.5 milliseconds that I was hoping for. And we get, so here's sort of, this is the same graph as that one, just for our potential. And we get very similar accuracy to gap on each individual individual property. But there's a lot more work we have to do here to make this practical. And I really want to focus now for the next 20 minutes on the spatial decomposition that I was talking about. So this is the question again. And this is one of the key ingredients. Without that, I can't develop this approximation theory. Without that, we shouldn't be trying to fit into atomic potentials in the first place. Very similar questions arise in virtually all branches of coarse-graining material models, I should say. So this is not just specific to this question here, but it nicely illustrates why it's important. Okay, so the question again is, suppose I start from an electronic structure model where the potential energy surface is given by first solving a nonlinear eigenvalue problem, and then as a function of the energy levels and possibly the orbitals. Should I be possible in the first place to approximate that by an interatomic potential of that form? In other words, does that have a spatial decomposition of that form? Okay. And when we started thinking about this a few years back now, we thought we'd start with the simplest models that are still non-trivial, namely tight-binding models. The problem, DFT, initially we thought, okay, let's start look at this with DFT, but the problem is there are so many mathematical technicalities in that would take us years and years to get around. So we start with something simpler to just understand the basic principles. And it turns out there are sufficiently many interesting questions in there, and we can focus more on the conceptual challenges. So, and I'll get into more details about under which conditions this result is true, but for now let me again state this sort of in general, make this a general statement. So the statement is that for a variety of electronic structure models, we can prove the following result, that this quantum potential energy surface can indeed be written as an exact spatial decomposition. So I can write exactly that this potential energy is a sum over individual particles, and then each one of them has a site energy contribution. The only difference now between this expression and that is here I have a cutoff, so this function v depends on a small interatomic neighborhood. This function vqm depends on everything. So in what way is that a spatial decomposition? It's this locality. So I can estimate how strong the dependence is on the far field. Okay, so I can say if I'm sitting on my atom I right here and I'm perturbing an atom j far away, then the site energy here will not change much. And I can estimate how much it will change. Okay. And in addition, you get all the right symmetries. So you inherit the permutation and rotation symmetry of the total potential energy surface, which is exactly what we used in the approximation theory before. Without that, I can't carry that out. And it's analytic. And that's another thing I used in the approximation theory without mentioning it. So these site energies, they inherit the smoothness, they inherit the symmetries, and they are local. Okay, so now this can't always be true, right? Because we all know there are things such as Coulomb interaction and so forth, and those are the kind of things we turned off. Hopefully I'll still get to some difficult questions in a moment. Okay. So let me first explain, therefore, how this is proven in principle and why it's not an entirely trivial question. So the tight binding model that I'm starting with is this one. Okay, I have nuclei positions. I take these as input into a Hamiltonian operator. And I'm assuming that the off-diagonal elements, the hopping terms, they decay exponentially. And I'm all here in this first case, I'm going to get to something more complex in a minute, but in this first case, I'm also assuming that the diagonal terms don't depend on the environment. And essentially, you can think of what I've done here as a screening assumption. I've assumed that all Coulomb interaction has been screened out. Okay. Now, if I have this, okay, I can solve the electronic structure problem, and then I can evaluate the potential energy surface. And it's not so important what that function g here is, except that it's analytic. So typically, you take, it depends really on your context, whether the electrons live in a canonical ensemble or grand canonical ensemble. For materials, which is what I do mostly, grand canonical is really the correct choice, but so then that's your function. All right, so that's fine. So now, how can you get this? Here's my question again. How can I get this decomposition? Right? How can I convert this sum over energy levels into the spatial decomposition?
I'm not missed something because
Yes.
I'm not familiar. So the left-hand side depends on the position, and the right-hand side, how does it depend on the position?
Here. So what you stick the positions into the eigenvalue problem. That gives you the energy levels, and then you stick the energy levels into that sum.
So this is just some matrix multiplication and the eigenvalues?
Did I
It
make a
depends on
mistake
R.
here? So I'm starting with the R.
Yeah, I see.
I'm
Yeah,
evaluating
so
the
at
Hamiltonian.
each position, it's a matrix. I see. So
Yeah,
it's
yeah.
just-
The H of R is a matrix, that's right.
Right.
Then you solve the eigenvalue
Yeah,
problem,
okay.
and then the
Okay.
eigenvalues,
Now
the
I
energy
understand.
levels give you the potential energy surface. Okay. But I mean, the key point here is that the energy levels, the eigenvalues are global objects. Right? So they depend on the entire configuration. Now, if I chop my configuration in half and throw one away, then I'm going to get a completely different spectrum. So how can something like that be true? And the answer is surprisingly simple. Once you start thinking about this, you find quickly in the literature what the main ideas are. This is again not my idea. This is quite old actually. This is just how I would reformulate it in a simpler language. But basically, what you observe is that this here is just a trace. Right? But it's a trace after you diagonalize the Hamiltonian. So now the trace doesn't change if you change coordinates. So all you have to do is, instead of evaluating the trace here, you can evaluate the trace there in real space coordinates. Okay? And a trace is written in these coordinates is nothing other than a sum over atoms. So I'm slightly oversimplifying, but not very much here. Okay? So basically the diagonal elements of this matrix, so G of H, G of the Hamiltonian, this should be a G beta, apologies. The diagonal elements of that matrix, those are my site energies. Okay. That's in a way, that's all there is to it. Okay, so now that gives you a decomposition. Now I still have to prove that it satisfies the properties that I stated. Namely the locality, that's what I'm after. And so for that, what you do is you switch to different representation. You go to resolving calculus. So because this G here is analytic, we can write G of H as a contour integral. Okay, so here's let's say this is the spectrum of H, or somewhere along here's the spectrum. Then somewhere there are singularities of G, here and there. So I take a contour that avoids the singularities but surrounds the spectrum, and then integrating G times the resolvent gives you that matrix function. Okay, so it's a standard trick. And then the nice thing is that these resolvents here are extremely well understood. So if you're familiar with these sort of estimates, you know this anyways. But so one analog would be if you take a Laplacian with a mass term, a positive mass term, then you get an exponentially decaying Green's function, and that's what goes in here as well. That's what when you put that together with a few other things that are not very difficult to carry out. After a bit of work, you then get the estimate that I mentioned, that these site energies that I've defined here can indeed be estimated like this. Right? So what went in here is that I assumed that the Hamiltonian H is local. If I don't have that, then I can't get that estimate. And secondly, I really need to exploit that this contour that I use to evaluate that matrix function stays away from the spectrum. Those are the two properties that I need. Or rather, what I need is that the resolvent is localized as well. Those two are somewhat equivalent statements. Okay. And this is sort of where things go wrong very quickly when you start looking more closely, because this is a purely qualitative estimate. So specifically, the issue that you quickly learn is that the first singularity here is order 1 over beta away from the spectrum. Beta is the Fermi temperature. And you have to look at the units and so on and so forth, but in truth, this constant is very small, and even though you get this exponential decay, if you plot it, you can barely see that it decays, right? So something like this, and all right. So it's a qualitative estimate, but it doesn't tell you quantitatively why you see locality of interaction. Right? And I'll come back to that in a bit. So this is in metals. So a different class of materials, insulators. Here you have a bit more structure available. So in insulators, you assume you have a band gap. So now let's take, what you can do now basically is you can replace this contour that's supposed to avoid the singularities, but just a contour around the occupied band. And then the distance to the spectrum is, well, basically the gap. And we can then show that in this case, the constant here in the estimate is proportional to the gap. And that is actually a very good estimate. So I unfortunately didn't have the data on me when I was preparing the talk, but we tested this on silicon, and the prediction we make here, the analytic prediction and what we see numerically matches very, very, very well. And the interesting effect here is because if you have a pure band gap, that's actually quite rare. When you're trying to do real material science, you put defects in, and you have surfaces, and I don't know what else could happen. And that pollutes, that really pollutes the spectrum, especially in particular pollutes the gap. And so now you think, well, okay, so now what's my gap? Is my gap now this thing here or that? Because if it's that small thing, then you're lost again. But it turns out that doesn't matter. So you can actually prove that the point spectrum polluting the gap does not affect this estimate. Okay, so and so at least for insulators, tight binding models for insulators, we're quite confident that these estimates that we have are really close to what you really see in practice. Okay. And maybe there's one more comment about this, is that what does this have to do with localization of wave functions? And I'm not sure very much. And so the continuous spectrum is completely delocalized. But what goes into the proof of that last point 3, that this constant here depends on the big gap, is that the point spectrum is the eigenfunctions corresponding to the point spectrum are of course localized. And in fact what we prove is, implicitly, I don't think we ever write it down like that, but that each of the corresponding eigenfunctions decays with the same rate. So it's the gap in the continuous spectrum that determines how fast these eigenfunctions decay. All right. So this is what we know for simple tight binding models. I think I might skip this. I can show it quickly. So basically, to prove this is very not so difficult. You just say you decompose the Hamiltonian into a Hamiltonian of a homogeneous system without defects, and then that gives you the continuous spectrum, and then the correction that comes from a defect is because the defect is a localized object. It's a finite rank correction, and then you can stick this into some standard linear algebra identities, and you put in the resolvent estimates again, and everything just pops out for you. So conceptually, this is quite easy. There were a few details that we had to be careful about, but that is the main idea. Okay. Then there's maybe one more case I want to mention here before I get back to metals, which is nonlinear eigenvalue problems. So until now, even if I didn't say it, I always thought about linear eigenvalue problems where the Hamiltonian depends only on positions, but it doesn't depend anymore on the orbitals or the energy levels. Okay, so here's a simple simple toy model, a nonlinear tight binding toy model. We add a potential to the diagonal, which depends on electron density, which is defined in terms of the orbitals. But other than that, the model remains the same as my tight binding model. And in this case, literally everything I've told you until now remains true, provided that the dielectric response operator is stable, or rather this I minus L. L is the dielectric response operator. So basically, what happens is you now need to know what happens to the electron density if you perturb the nuclei. So you write down a linear system for perturbations of the electron density, and if that linear system is a stable system, then you linearize your arguments and everything works out again. And the only point to make here really is that this linear operator here is one that makes physical sense. So basically, these operators, the stability of that operator, you would always expect to have that in practice, because otherwise your electronic structure becomes unstable. You have small excitations of the electrons, and they would just blow up your system. So that, since that doesn't happen, this operator must be stable. Okay. And then you get similar results again. Okay. So that nonlinear eigenvalue problem is okay as well. Right. So this is now maybe the last point now. I forgot I was going to add that. Everything up to here was tight binding models. Now the question is, can one still do something similar for PDE models, namely Hartree-Fock and density functional theory are the ones we've been looking at. And so for a screened Hartree-Fock model, my postdoc and PhD students, that at some point they sat down and they went through all the analysis and said everything works out. They want to write it up. Still today they haven't, but the proofs seem to check out. So it looks, the fact going from tight binding models to PDE models is not really an issue. The real challenge when you go to honest DFT models is the Coulomb interaction. How to understand the screening of the Coulomb interaction, I can't, yeah, we're not really anywhere nearer to doing that, I think. But we can test it numerically. So for example, this test here is for bulk silicon. What we did here is we just took large slabs of silicon. We solved the DFT equations, Cauchy DFT equations, and estimated the so there is a site energy you can define in that way, and then you can just numerically estimate these derivatives, which we claim have to be exponentially localized. And you can see that at least definitely pre-asymptotically that looks convincing. And then eventually you reach the accuracy of the DFT solver, and you can't be sure anymore what is what, but it looks like the results don't really change much here either. Okay, but now metals finally. So that is now the part where I have very little to say. But this is it's in a way the reason why I'm here, because I thought I have to listen to how people talk about localization. What can one say? What are the techniques that are around? Because metals are the one case that that are really easy to fit in practice, and where I have no good starting point to explain why that is so successful. Okay, so on the next slide, I will show you some numerical tests, but I'm not doing that for site energies anymore, because these are quite involved to evaluate. So instead, what we're testing is locality of forces. So if the force acting on an atom is just the derivative of the quantum potential energy surface with respect to the atom position, then what we're asking is whether the forces are local objects. So rather than the energy, we're looking just at the force. And this is much easier to evaluate. But it's a necessary condition. So without that, you cannot have locality of the site energy either. Okay, so here's our first test. This is now for aluminium. Take a large slab of aluminium in the ground state, and then you compute the force on one atom, which is 0, of course, because it's in the ground state. But then you perturb an atom far away, and you see how does this force change. There, you got a flat line. So basically, this is completely non-local. Everything interacts with everything. And that corresponds to what I said earlier, right? That this decay goes with 1 over Fermi temperature, and if the Fermi temperature is 0 or near 0, then you just have this flat line here. And so I started asking around. I started asking people, why don't you see this in practice? What really happens? They said, oh, it's just Anderson localization. I don't believe that, I should say, but this is the standard answer I got. So it's this order. We never do metals in ground state. Right? It's always at some finite temperature. And the key point is this is not the Fermi temperature we're talking about, but now this is the ionic temperature. So the next test that we did, therefore, is we took an interatomic potential. We ran an MD simulation, and then that way we got random samples of this metal slab. Then we evaluated the DFT forces on these random samples, and first at 50K ionic temperature, and then 500K ionic temperature. And you get, well, it's at 50K, you get first a nice big drop in the force, then flat again. Decrease the temperature, so now we're now already well above room temperature. We get an initial nice big drop in the force, this is what we're hoping to see. And then it's flat again. And, well, that I like, right? This is what we wanted to see, that the higher you go in the temperature, the further this drop goes, the more locality you gain. And I should say this must be well before the Anderson transition. I cannot believe that at these temperatures you have localized eigenstates. I certainly didn't find any, and if somebody tells me otherwise, I'd be curious to hear. But so there must be a simple effect, I think, but I don't know what it is. We thought maybe DFT is too complex. Maybe there's too much playing going on there that we don't really understand. So we tried exactly the same simulation with tight binding, but the result was exactly the same. Okay, so 0 ionic temperature, 50K, 500K. So I don't really have an explanation what these flat pieces are, and I also don't have an explanation why they don't matter, because this is what my friends, the material modelers, keep telling me. That doesn't matter. It's this initial drop, that's all it is. But if you have these long-range forces in there that you can never sum up, then how can that not really just destroy your simulations? So anyways, we thought, okay, let's make the problem even simpler. Let's go to an actual Anderson model. And that is what a friend of mine suggested. This would be the simplest one to understand. That sort of more or less mimics what I want to see. So now I have the Hamiltonian has the hopping terms and the potential. The potential is given in terms of a Yukawa interaction and some random charges. And the randomness in these charges models my ionic temperature. And so now I finally see the result that I really wanted to see. So at near 0 temperature, I get this very slow exponential decay, which comes from the Fermi temperature. And then as I increase the ionic temperature, the decay sort of consistently improves. So there seems to be a result here that I actually don't know yet how to prove that rigorously. I'd be interested to hear what sort of techniques one has available. And then I would really love to know how I can connect this up to this, because I have no idea what it is that we're missing. Possibly the correlation. Because here we have uncorrelated randomness. In the examples before, there's a very strong correlation between the Hamiltonian entries. Okay, so these are all just sort of vague problems that I have that I'd love to talk to anybody about who's willing to listen. Otherwise, I will take them home with me again. And so let me just put the last slide up to summarize quickly what I talked about. So the question that interests me is not so much the localization of the wave function of the electronic structure, but rather of the resulting mechanical response. And that's a question that is, for some reason, discussed a lot less. People use interatomic potential, people coarse-grain electronic structure models all the time without really thinking too much about that, I think. There are very few people who have thought about this in the past. And I'd like to really understand that better. and here are a few points, but specifically the one problem that bugs me most that I can't get a handle on is why in conductors, what is really, what are the features in conductors? What are the properties that I can use in order to establish results like that? Maybe it's randomness, but I don't, missing the tools how to do that well. So I'll stop here and thank you.